So starting this set of discussions today, we will see the structure of electromagnetic field in terms of field theory, and then we'll see its quantization in the way we have seen the quantization of a scalar field as well as for spinor field. Okay, so in order to go up to the phase space structure, the Hamiltonian and other things, we need to know the Lagrangian, and whether before that we will need to write a structure which is Lorentz invariant as well. Whatever we demanded for scalar field and spinor field should be true here as well. So let us start recapitulating the ideas which we learned at the standard electrodynamics level. We know that the working formulae governing electrodynamics are governed by something called the Maxwell's equations. Maxwell's equations have two separate set of information for electric part and magnetic part. In presence of material, charge and currents, these four equations are collectively named as the Maxwell's equations. Now, the Maxwell's equations are just collections of four set of equations. They are not four equations themselves, because we have two scalar equations. So these are scalar equations which one component each, one equation it is. However, there are two vector equations. So these are three equations in themselves. X component, Y component, Z component should satisfy this equality, and similarly X component and Y component and Z component should satisfy the other identity which is being said about. So these set of equations govern the whole of electrodynamics as far as we know. Now, had it been the case we were discussing about electrostatic theory and magnetostatic theory, meaning there was a divide when things were not talking to each other, then magnetic field will not be varying in time, it would be put to 0, and electric field will not be varying in time, and that would be put to 0. So that was statics, electrostatics and magnetostatics. When that happens, you see that the curl of E is supposed to be 0. If curl of E is supposed to be 0, we know that it can be happening through a gradient class vector. A vector which is made from a gradient of a scalar will always have its curl 0. Okay, but the curl of magnetic field is not supposed to be 0 in presence of current. So therefore, magnetic field will not be a gradient class vector. So curl of E was always supposed to be 0 in electrostatics. Divergence of B was always supposed to be 0 in magnetostatics. So therefore, this is better a gradient class vector. We typically write it as in terms of minus gradient of phi, such that curl of E is 0. Similarly, for B to always have a 0 divergence, it should be a curled class vector. This should be a gradient class vector, and magnetic field should be a curled class vector, because a vector which is made from a curl of another vector will always have its divergence 0. So therefore, in electrostatic and magnetostatic respectively, magnetic field and electric field are to be obtained from potentials. Scalar potential for electric field, whose gradient will give me the electric field, and vector potential for magnetic field, whose curl will give me the magnetic field. Once we go on to the theory of electrodynamics, these equalities break away. No longer electric field and magnetic fields remain in isolated sectors. Electric field and magnetic field start talking to each other. Namely, curl of E is no longer 0. It is equal to the minus of the time derivative of magnetic field. And similarly, curl of magnetic field in some sense is also related to the curl of electric field. Remember, the displacement vector D is related to the electric field in terms of the epsilon naught going to some epsilon relative times epsilon naught. That is, the polarization is taken into account. You should go back and look at the notes of your electrodynamics to see the structure of these equations. But as we see in electrodynamics, these isolations were not working. This will no longer be 0, and this will no longer be without free of electric field. The causality in this is that once we have put on a magnetic field on the right hand side of the curl of electric field, then curl of E is no longer 0, and therefore we cannot say that it is a gradient class vector, which was true only for electrostatics. Electrostatics right hand side would have been 0, and then we will have demanded that it is a gradient class. Now we don't. However, divergence of B is supposed to be 0 still. Even when electric field and magnetic field talk to each other, they talk through their curls. B feeds into the curl of E, and E feeds into the curl of B. So divergences are left alone. So magnetic field's divergence still remains the same, that it is 0. That means still magnetic field can be a curl class vector. electric field can no longer be a gradient class vector, but magnetic field can still be a curl class vector. So therefore I can write down the curl of E is minus del del T of B, and where B is a curl of some quantity. I can bring this object onto the left hand side, and therefore I will have a curl of E plus the time derivative of A is equal to 0. So you see, now in electrodynamics, when things move and change, curl of E is no longer 0, but curl of E plus del A upon del T can be 0. So therefore, this whole vector can be a gradient class vector, unlike electric field alone. If del A upon del T was 0, then electric field indeed would be a gradient class vector. If it is not, then the combination of E plus del A upon del T would be a gradient class. So therefore, I can put back the del A upon del T on the right hand side, which initially I had stolen from the right hand side itself. So therefore, electric field in the electrodynamical case will no longer be only a gradient of phi, but gradient of phi along with the temporal derivative of A, the vector potential. So electric field is made up of both scalar potential and vector potential, not vector potential, not scalar potential alone. Magnetic field, on the other hand, is made from only the vector potential. Okay, so we have now four kinds of potential. One is the scalar potential phi, which is a singular object, and three components of vector potential. So together we have four potential: phi, A1, A2, A3. All right. So now we know the first equation again remains like this, untouched. And if we are talking about things in vacuum, then effectively there is no difference between the displacement vector D and the electric field E. So I can simply write divergence of E is rho times epsilon naught. Okay, there is no material, so all the rho is the free rho. On the Maxwell's equation side, there is a rho free charges should appear here. Polarization charges are taken out of the game. Total electric field depends on all sort of charges, free charges as well as the polarization charges. But if there is only vacuum, there is no material, electric field will be talking to only the presence of free charges. So I can write it like this. So therefore, I know that the divergence of E should be rho upon epsilon naught, and therefore I can take the divergence equation of the first box equation which we just derived. For electrodynamical case, as we have learned, in the case of dynamics, when the things are not statics, extra term del A upon del T gets added to the definition of electric field from its potential. And now we know that in vacuum, divergence of E should be rho upon epsilon naught. So therefore, divergence of the whole equation should be equaling to rho upon epsilon naught. So when I take the divergence, this term gives me Laplacian of phi. While the divergence is the spatial derivatives, there is already a temporal derivative acting on the vector components A. So the divergence involving the spatial derivative will commute with the del T, meaning temporal derivative. It doesn't matter which order you do. So I can take the spatial derivatives first and wait for the temporal derivative to act later. In this way, the divergence operator goes inside the del T operator. So I will have a divergence of A inside. And that better should agree to rho upon epsilon naught because of the Maxwell's first equation. Okay, this is so far so good. Now let us look at the case of the Maxwell's fourth equation in vacuum again. If I vacuum in the sense of we are talking about standing at a point where there is no material, we are not looking at a inside a material, we are looking from vacuum and there is some charge and current flowing from here. Had we be standing inside a material, then the H and the D would have been different from the E and the B. But if we are standing in the vacuum looking at the moment of motion of the charge and the current, standing in not inside a material but standing in the vacuum, then E will be equivalent to D and H will be equivalent to B. So therefore, the fourth set of Maxwell's equation, what we can see, since magnetic field is already curl of A, which we have established, so therefore this equation is curl of A. And I can bring this equation on the left hand side saying that D is equivalent to E. So I will have a minus of mu naught epsilon naught del E upon del T, and I will be left with mu naught J on the right hand side, which is this. And again, simple algebra of the curl and the gradients and whatnot. You know from your electrostatics or electrodynamics course, curl of a A is equivalent to gradient of divergence. This will be a scalar. Divergence of a vector is a scalar. Therefore, scalar's gradient will generate for me a vector. This is whole thing as a vector minus Laplacian of A. This is again a vector. So curl of a A is supposed to generate a vector using the identities of the differential vectors computation. You can obtain that curl of a is gradient of its divergence minus Laplacian of A. And this object del E upon del T is just definition of E, which was obtained over here, should be fed into this equation. So I will have a mu naught epsilon naught del T, and the electric field will be written like this, which we have obtained in the first box. So far so good, and right hand side will be left with mu naught J. So this looks all right, that we have consistently written Maxwell's equation for an observer standing in vacuum looking at the motion of charges and currents. So the whole magnetic field generated by the motions of current as seen by this observer standing in vacuum can be expressed by this equation. You can see that there is a term which is a gradient. Gradient is appearing here and gradient is appearing here. So I will collect all the gradients. So gradient one term will be divergence of A, which is coming from the first, and the second term will be with a plus sign coming from this part, del phi with a minus sign, and a minus sign is already there. So together they will add and make me mu naught epsilon naught del phi upon del T. Okay. And then there is a Laplacian part which is minus del 2A, and then there is a del T which will go and hit this term, which will make it a double derivative of A. Again, a minus sign here and a minus sign here will combine together to give me a plus and mu naught epsilon naught. So ultimately, simple enough algebra will give you that the potential which generates the magnetic field satisfies this equation, this equation at the end. This is the equation satisfied by vector potential A. This is the equation, the second box equation is the equation satisfied by the scalar potential phi. So together they are supposed to generate magnetic field and electric field. So I know now how these fields change in space and time individually, and then I will try to see how we can construct more things out of it and what is the structure which is hiding behind. On face of it, there does not look like to be a very clean story where we can identify, but wait for a minute and we will see that these two equations are more telling than what they appear as of now. Fine. So let's just go forward and see what is there in our hand to do. First, let us see there is a symmetry which is hiding in plain sight. We knew that magnetic field is supposed to be curl of some vector. What is that vector? We do not know, but we know that that vector satisfies this equation in tandem with phi. So phi and A are having mixed equation. Dependence of phi, spatial dependence of phi cares about the temporal derivative of the divergence of A, and spatial derivative of A cares about the divergence of the temporal derivative of phi, vice versa. So they are coupled equations. However, there is a structure which we already know, that magnetic field is to be solely determined by A. Electric field was to be determined from both phi and A together, but magnetic field is only the story of A. And then if A has a particular symmetry, that means A, if it is changes by some gradient of some other function, some unknown function, then magnetic field does not change at all. So B remains the same. This is because when curl of is going to go and hit this whole object, curl will hit this gradient of f as well. But we all know that curl of a gradient is 0 for any function. So in principle, give me a function A which generates, give me a vector A which generates a magnetic field for you. I can add any gradient of any function. Still A will change, magnetic field will not. So therefore, this is called a gauge symmetry. So this symmetry is called a gauge symmetry, where I can change my A without changing the magnetic field. Okay, but this is not complete story. In electrodynamics, I know that A also determines electric field as well. So only magnetic field does not change would not be story of electromagnetic field does not change. Only magnetic part is not changing. So I would want electric field also to remain invariant under this transformation. Whatever keeps magnetic field intact should leave electric field also intact. And that can be done only if I demand that if A changes by gradient of F, phi should change by temporal derivative of F. A is changing by spatial derivative of F, and phi should change by temporal derivative of F. Then only you can see if that happens, the electric field also does not change, because there is a gradient of phi and then there is a del A upon del T. Together their negative sign will give me the electric field. If A changes by A goes to A plus a gradient of F, then the temporal derivative of A will change by temporal derivative of A plus temporal derivative of the gradient of F. And if I demand phi changes by negative of temporal derivative of F, the gradient of phi will change by gradient of phi minus gradient of temporal derivative of F. And this spatial derivative and temporal derivatives order can be swapped. So I will get the exactly negative term which is coming from this part, and they will cancel each other, and therefore electric field will also not change. So therefore the gauge transformation is a statement that we have a freedom to change A by this amount and change phi by this amount. That I choose a function f whose spatial derivatives will go and shift my vector potential, whose temporal derivative I will go and change my scalar potential. And neither the electric field and nor the magnetic field will change under this process. So this is called gauge invariance. So if I demand this to happen, which is minus of which is the electric field, I should allow for phi to change like this. So therefore I have a symmetry that A can be changed by this amount, phi can be changed by this amount, and together neither the electric field nor the magnetic field changes. So if I have a freedom, how can I use that freedom to my good business? Since I have a freedom to change my A and change my phi by some functions derivatives, let us see how does that help. So I can make the changes in A. A has to change by A plus gradient of F, and phi has to change by phi minus del F upon del T. Now suppose I am looking at this quantity, divergence of A plus 1 by c square divergence time derivative of phi. Under gauge transformation, how will it change? It will change as Laplace. So divergence of A will become divergence of A plus Laplacian of F, and the temporal derivative of phi will become temporal derivative of phi minus 1 over c square del 2 F upon del T square. So that means under the gauge transformation, this object changes from its previous value through a Laplacian and a double time derivative of the function. And suppose initially this number was something, divergence of A plus 1 upon c square del phi upon del T was some other function g. If I choose my f that this net change here cancels this g completely, that means I demand that the Laplacian of f minus 1 over c square del 2 upon del T square of f is exactly the negative of g, then I know under the gauge transformation, the new a's and new phi, which have changed by this much amount, they have become this, they will make the condition divergence of A plus 1 over c square del phi upon del T is equal to 0. Even if it was not 0, using a gauge transformation, I can land up to a case where this combination becomes 0. Why this is a useful combination? Because now you see, if I can make this object going to 0, go back a couple of steps, you see this function was exactly appearing here. Mu naught epsilon naught, remember, is 1 over c square. So divergence of vector A plus 1 over c square del phi upon del T. This object could have been anything, But now we know if it is anything which is non-zero, I can do a gauge transformation. I can rechange my A to something A plus something else, rechange my phi to phi plus something else. Under this process, this object will not change, magnetic field will not change, but this can change by some amount. How much amount? This much amount. And if I choose my this much amount, that exactly cancels its previous value. That means after gauge transformation, I will get up a new A and a new phi, which are these and these compared to the previous versions, which satisfy that this object is zero. And once this object is zero, we see where it appears. It appears over here. This term whole becomes zero, and I have a Laplacian of A with a minus sign plus 1 over c square, the double derivative of A with respect to time, is equal to mu naught j. Okay, so you will get using that that minus of Laplacian of A plus 1 over c square del 2 upon del t square of A is 0, or is mu naught j. The magnetic field component now becomes this. They become independent of phi. Previously they were dependent on, their evolution was dependent on phi due to presence of these terms. So now I have killed the whole term. Now it has become independent of phi. The similar thing you can do for the phi itself. Phi's evolution was also entangled with the A's appearance. So now what I can do, since I have used a gauge where divergence of A is minus of 1 over c squared del phi upon del t, I can use that fact into this equation and change this divergence of A as minus of 1 over c squared del t of phi. So overall, this equation also becomes 1 over minus of Laplacian of phi plus 1 over c square del 2 upon del t square of phi is equal to rho naught upon epsilon naught. Now this also now totally depends on phi. So I have decoupled those A and phi's by doing a gauge transformation. What more? You can see that operators which are appearing hitting on phi, which is Laplacian with a minus sign and double time derivative. Laplacian with a minus sign and double time derivative. And if you remember, this is our definition of D'Alembertian. So ultimately, with a minus sign actually, this is minus of a D'Alembertian. So I have the equation that D'Alembertian or box of phi is equal to minus rho upon epsilon naught, and box of A is minus mu naught j. So together we have equations like box is something and box of A is also something. And now we will see that this box story becomes more interesting if I try to write things in terms of special relativistic coordinates. So in order to go and relate things with a special relativistic 4 vector notations, which we are typically familiar with, I see I have 4 things in hand. One is phi, scalar potential, and 3 components of vector potential. I can write them as a collection of 4 objects. Whether these 4 objects are 4 vectors or spinors or what, we have to determine that, because we have seen collection of 4 objects do not always become vectors. We saw an example in previous set of lectures. Collections of psi1, psi2, psi3, psi4 was a spinor. Similarly, arbitrary collection of 4 numbers does not become a 4 vector. For example, I can take t square, x square. This is not 4 vector. Any 4 collection of objects will not be a space-time vector. So we have to determine, if I write down this phi and A together as a 4 component object, how does it transform under Lorentz transformation? Just like we try to obtain how does the spinor size transform under Lorentz transformation. In addition to that, again we have on the right hand side collection of 4 objects. One scalar charge density and then vector charge density or current density, which we call. So in addition to phi and A, we can write down rho and j as well. So I have a collection of 2 4 component object. This is 4 component object and this is also 4 component object. But we do not know whether these 4 component objects are scalar, meaning 4 independent scalars or 4 components of vectors or spinors or any other thing, or maybe nothing. They do not transform. They are just a random collection of 4 things. So for that to happen, I will try to recast this equation in a more evident way and try to see what happens. So in order to do that, I just divide the first component by C and multiply the first component of the current density into C. So let us call it this 4 potential or 4 vector potential and this 4 current density. Okay, so 4 potential and 4 current density we are interested about, and we want to know whether this collection, which is named thusly, is a good vector, spinor or scalar which transforms appropriately under Lorentz transformation or not. So I have divided the first component or zeroth component. Let us say this whole collection is going to be called as a mu, a0, a1, a2, a3, without saying that a mu is a component of vector. I'm just randomly naming the 4 components. Similarly, the 4 components of the current density are going to be called j mu. So I divide the first component, first meaning zeroth component of a by c, and multiply the zeroth component of j with c, such that the two set of equation, which was box of phi, which was a scalar equation, and box of a, which was vector equation. We have 3 components. Ax will satisfy ax is equal to jx, box of ay will be mu naught times jy, and box of az will be mu naught times jz. So this is 3 equations here and 1 equation here. If I make this multiplication and division through c and use the fact that c square is nothing but mu naught epsilon naught, then you can see the 2 box equations together can be written as a single box equation like here. Box a mu is equal to mu naught j mu. Put mu is equal to 0, put 0 here as well. Relate that a0 was phi upon c and j0 was c rho. You will get a box of phi upon c is equal to minus mu naught c times rho. Take this c over here, so it will become c square without c here, and c square 1 upon mu naught epsilon naught. So this object will become minus rho upon epsilon naught. This is the first equation. And remaining 3 equations are untouched. A1 is A1 here, J1 is J1 here, A2 is A2 here, J2 is J2 here, J3 is A3 is A3 here, and J3 is J3 here. So therefore, I do not have to worry. After this just simple multiplication, I have converted the set of equation into one seemingly compact equation. And I want to now know whether these things are 4 vectors, 4 components of a spinor, 4 random scalars, or some weird object which we have encountered. In order to know that, let us look at the right hand side first, j mu. Okay, again j mu has 4 components, rho and the 3 surface current density. Okay, in order to know how these components transform, let us look at a case where suppose there is a frame S prime in which a person is standing and looking at a stationary charge with respect to this guy. So therefore, this frame S prime, the observer sees that there is a there is a charge density, static charge density, which he or she is going to call as rho prime. So this observer says that there is a stationary charge density rho prime, and there is no movement of the charge. All the charge is static, nothing is moving according to this guy. So therefore, they will declare that there is no current density, J prime is 0. Now look at the same story being viewed from another frame S, which is, let us say, lab frame, and this observer says that the whole box of this observer and the charge is moving. So there is S frame, S prime is moving with respect to S with a velocity v, or parameter beta. Beta, remember, is v by c. So c times beta will be the speed of the frame S prime with respect to S. So beta is just a compact notation of how fast the frame S prime is moving with respect to S. Now what is the story according to the person in the frame S? The person in S frame will see there is a moving charge, a charge which is moving with certain velocity. So they will say that indeed there is a charge, and therefore a charge density. Suppose this guy was standing in a box. S prime was in a box. S also sees there is a box and there is a charge inside, so therefore a charge density inside. But they see that there is a velocity to the charge, so there is a current as well. So S sees both charge density as well as surface current density. S prime only sees charge density and no surface current density. Now let us see what are their magnitudes. So first of all, this guy S prime will say that according to him, there is a charge dq upon d3 v prime, where d3 v prime is the volume of the box around him or her. Now, the same story when viewed from the frame S, they will also say that, okay, there is a charge inside a box, but they will disagree on the amount of the volume of the box, because the x-axis is a boosted thing, y and z axis do not change. So overall length will change with this factor, and x and y will not, the y and z directions will not change. So overall the volume of the box seen by S prime will be d3v prime, seen by S will be d3v, and together they are related by this 1 minus beta square root factor, 1 over gamma factor in more compact notations of special relativity. This is all right, because according to Boost, one arm will be contracted and therefore volume will also be contracted. So therefore, if the S is looking at the volume being contracted, both of them agree that how much charge is present. If one particle is present, both of them will agree that one particle is present, and charge is a fundamental unit, fundamental property of object. They will all say that net amount of charge is unchanged. Only thing changing is volume description. So according to S, the same amount of charge is now living in the volume which is slightly shorter, d3v, which is related to d3v prime by this extra factor. Therefore, the charge density which was declared as dq upon d3v prime by observer S prime will say that this much charge remains invariant, but this much volume, so rho prime. So you see the charge density has changed by a factor rho prime upon 1 minus beta square. So S and S prime do not agree on the notion of the charge density. Secondly, how much of current this guy sees? S sees there is a current, which is the charge density what it sees and the velocity with which the charge density moves. Remember, J is always rho times V. So now we have obtained the expression of rho what this guy S sees. The V will be just beta times C. Now write down the things. Rho is previous rho prime, the charge density as seen by S prime, divided by 1 minus beta square, and you see there is a nice structure which emerges out, which, if you pay close attention, is the same structure which we have seen before: sine hyperbolic alpha times rho prime and cos hyperbolic alpha times j prime. It so happens that j prime, jx prime is 0 according to S prime, so therefore this cos hyperbolic term does not arise. Only the charge density, gamma, and sine hyperbolic alpha, which is precisely this term. This kind of transformation we have seen before: sine hyperbolic, cos hyperbolic. This was exactly like the spatial vectors were supposed to transform. So it looks like that the Jx is indeed transforming as if it is component of a spatial vector. One can make this statement much more clear by this realization that, remember what was rho and what was C beta. So rho times C beta, C can be pulled out. Beta is just, C beta is velocity, let us say. So velocity is just dl by dt. So this C factor can be removed, let us say dl by dt. Okay. And while charge density is dq by d3v. So overall in the denominator, I have a d3v and dt. Put together, I have a d4x in the denominator, which is space-time volume. And if you remember our discussion in special relativity, d4x is invariant under Lorentz transformation. dt changes exactly in the opposite amount in which d3v changes, and they exactly cancel out. Therefore, d4x does not change. dq does not change, as we have discussed. So overall, jx will only change as if dl is changing in frame transformation. So now you see, indeed, jx transforms like a spatial vectors component. This is dlx. If I talk about jx, it will be length projection along x-axis. If it was jy, I will get dly, and ultimately there is an invariant piece times a spatial vector. So jx indeed transforms like a spatial vectors. And similarly, you can argue for jy, jg. So all the j, full j transforms like a spatial Lorentz vector, as the spatial Lorentz vector would transform. The coordinates will transform. The infinitesimal coordinate differences are supposed to transform. They transform like components of a Lorentz vector. This much we had learned before. What about the zeroth component, charge? Again, the same story. Charge, like write down the charge density dq upon d3v. I can multiply and divide by dt. So in the denominator, I will have a d4x, and this object again will be invariant, and I will be left with the charge density transforms like dt, the infinitesimal coordinate difference along the zeroth direction. So it also transforms like a space-time vectors zeroth component. This j is transformed like space-time vectors spatial components. Together, rho and j put together transforms like spatial component and temporal component of dt and dx or dl. So indeed, they are up to some multiplication transforming like space-time vectors, and that multiplication is invariant. So therefore, we have J mu, which is a collection of these four objects transforming like a space-time 4 vector or Lorentz 4 vector. So we have identified that the right hand piece transforms like a Lorentz 4 vector. So what about mu then? Can we play some similar kind of game and show that mu is also proportional to space-time 4 vector? We can do that, but there is an easier trick of seeing this through. Because if this equation has to hold, right hand side transforms like a 4 vector. This object transforms like a 4 vector. Then the left hand side should also transform overall as a 4 vector, out of which I have a box. And if you remember our discussion on the special relativistic operators, this box was supposed to be an invariant operator. So whatever is left with that should transform as a 4 vector in order to make things consistent. So I do not know why I have put a C. C can rest over here. This should not have been there, but anyway. So ultimately, left hand side has to be Lorentz 4 vector because right hand side already is. In the left hand side, I have a box operator which is invariant, which automatically makes a case that A mu transforms like a space-time 4 vector. So now we have both the pieces at our hand, that this equation, which was collectively written for electric field, magnetic field together going into a particular gauge frame, I have wrote down this equation, which is a 4 vector equation. It is not 4 random scalars, not spinors 4 component, but vectors 4 component. So this is indeed a space-time 4 vector, a genuine 4 vector. Okay. Now, the building block of the electromagnetic theory is A mu, because A mu constitutes phi divided by C and the 3 components of A. These together generate electric field and magnetic field for me. So the building block of the electromagnetic theory's component is 4 vector, electromagnetic 4 vector, space-time 4 vector A mu. What more? If I go to empty space, some observer is just looking at a plain electromagnetic wave propagating. The electric field and magnetic field are being generated by phi and A respectively, and they are satisfying the box equation. But suppose it is just a vacuum, no charge density, no current present, then the right hand side becomes 0. J mu becomes 0. If J mu becomes 0 in one frame, a 0 vector remains 0 in all other Lorentz frames. So therefore, I cannot generate a 0 to non-zero J mu through Lorentz transformation. So therefore, right hand side will be put to 0 for all inertial frame, all Lorentz frames. And I have an equation which is box of A mu is equal to 0. This is 4 equations, A0, A1, A2, A3. That means some equation for phi and 3 equation for A. Now you see this is already a wave equation or the Klein-Gordon equation, which we are familiar with so many times. So you see the potential which generates electromagnetic theory is a 4 vector. It has 4 components. All the components satisfy the Klein-Gordon equation, just like the 4 components of Dirac field were also satisfying the Klein-Gordon equation. So we can again hope to do the quantization in the way we had done the quantization of a scalar field. The same thing we tried for the spinor field as well, so bad that we ended up changing the commutator structure to anti-commutator to make sense of physics. Let us see what happens for this thing. We still have a Klein-Gordon equation. If I try to quantize it, can I do it in the usual way, or should I do it the non-usual way of an anti-commutator? Till now, A mu's are supposed to be real quantities. So it looks like, since I do not enforce that they should be complex quantity, I would get through with the usual quantization, and indeed that will happen. that this kind of scalar field, this kind of a vector field is very much tied to the scalar field's derivation which we had seen. Nothing goes wrong with this. However, we have to be alert to the fact that we have a vector equation at hand. It is a 4-component object, just like Dirac-Spinor, but unlike Dirac-Spinor, it transforms under lambda matrix itself, not with d lambda. Remember, d lambdas were generated by S mu nu, where S mu nu were made from gamma mu 1/4, while lambda is made from the M matrix, M mu nu, and these are just 1 0 0 1 kind of matrices all around. Both of them are 4x4 dimensional matrices, but they are not related through any unitary transformation. So therefore, they are different quantum sectors. If they were related by unitary transformation, you would have said, okay, whatever appears as a vector is just a unitary transform version of a spinor. They are not. So therefore, this object is qualitatively distinct from the 4-component object spinor what we have seen. And one last bit, which is additional in this case, this wave equation does not came out automatically like playing around with the equation, which happened for scalar field and which happened for spinor. We just operated certain operator on spinor equation. We got the field equation of Klein-Gordon directly. Here, we had to do some massaging to the equation. We had to land up on a particular gauge. This wave equation is not always true. This is true in a particular gauge. And that gauge has to be always go along when we try to quantize this theory. We cannot do the quantizing forgetting this gauge. If I want to do harmonic oscillator quantization, like Klein-Gordon quantization, I also have to respect the gauge condition, because in this gauge only, this equation holds. So if I'm going to do quantization in this gauge, I should be alert to the condition I had imposed in order to get the wave equation. And the condition I imposed that I will make this term which was appearing in the A's differential equation to 0. That means I have to do quantization of the electromagnetic field with one condition. This condition has to be respected. So this gives up a new set of things apart from the structure of a scalar field. This opens up a new space of something called polarization. So we have to be alert about that as well. And we will see that this condition put together is equivalent to certain scalar fields doing the harmonic oscillator business up to a condition which fixes the number of degrees of freedom of the photon. So gauge potential has 4 components. Ultimately, we will see that using all the gauge conditions and whatnot, we will end up with only 2 of components of this are meaningful, and therefore these are the 2 polarizations of the photons. And that is what we will quantize when we go to the quantum theory. Okay, so that we will do in the next class. From where we will start to write down a consistent Lagrangian and try to see what kind of phase space structure and Hamiltonian and other things emerge out of it. And then we will see how to impose this gauge condition along with the oscillator structure to get the quantization. Okay, so I stop over here for this discussion session. We will move on to the Lagrangian description in the next.